So the other way we can solve this problem is using our knowledge of mechanical energy. So in part A, we again have the same situation. The spring K1 connected to a spring K2 in series, connected to a block of mass m. The block is displaced a distance delta x, and we're asked to find the period of its oscillation. Now the way we're going to do it this time is we're going to find the total energy of the system, the total mechanical energy, and I'm going to assume that you now know how to find the effective spring constant of this pair of springs. As it turns out, when you have a valid effective spring constant, you can use that to calculate mechanical energy as well. So if you don't remember how to calculate the effective spring constant of a pair of springs in series, go back and watch the last solution video for this problem, and I do that derivation in that video, so you should be able to find it there. So the spring energy of the system is 1 over 2 times K1, K2 over K1 plus K2 times x squared, where x is the displacement along the horizontal axis, plus 1 over 2 mv squared, the kinetic energy of the block. Now since the only forces acting on the block are conservative forces, we know that the dt equals 0. And we can calculate that since we have a function for energy. We can calculate that. K1 and K2 don't change, so the only thing we need to differentiate for this term is x. So the 2 cancels out with the 1/2, and we get K1, K2 over K1 plus K2 times xv. In this case, the m is constant, and so all we need to differentiate is the v. The 2's again cancel out, and we get mva. Now since we have a factor of v on both sides, we can divide v from this side and v from 0, so the v effectively just cancels out, and we get ma plus k1, k2 over k1 plus k2, x equals 0. This is the same as x double dot plus k1, k2 over m k1 plus k2 times x equals 0. And of course, we know that we can find the period by simply taking 2 pi times the square root of the inverse of this coefficient, which is m times k1 plus k2 over k1 times k2. We can now do exactly the same calculation for part B. Again, we have a mass m connected to a spring k1 on one side and a spring k2 on the other. In this case, the energy is going to be 1 over 2 k1x squared plus 1 over 2 k2x squared plus 1 over 2 mv squared. Because when the block is displaced a distance x, both of the springs are also displaced a distance x, or are compressed and stretched a distance x. And so differentiating this, we get the edt equals k1xv plus k2xv plus mva equals 0. Again, all of the v's cancel out, and we get mx double dot plus k1 plus k2 times x equals 0, which gives us x double dot plus k1 plus k2 over m times x equals 0. And our period for this system is going to be 2 pi times the square root of m over k1 plus k2. So this is simply a different way that you can do this problem. You can differentiate energy if you know that it's conserved, and then you find exactly the same differential equation for harmonic motion, and you can do exactly the same calculation to find the period of the system.